Hello everybody, this is your Abhishek sir, class 11th. Here's a video for you on the chapter work, power and energy. Three headings we have to take into account in this particular topic: work, power and energy. First of all, we'll be studying each of the headings simultaneously, and later on we'll try to develop or we'll try to see if there is a correlation between them, right? So among these three headings, the first one is work. Not wasting time, let's start with work. When do we say a work has been done? When do we say a work has been done? We say work has been done if there are two conditions required, na? Work has been done if a force acting on an object, produces a finite displacement. Force acting on an object produces a finite displacement. If the displacement is zero, no work is done. See, for example, if you are pushing a wall and the wall is not moving at all, so it doesn't matter how long you're pushing the wall, the work done by you will be zero, since the displacement produced is zero in the wall. That means if you're applying the force, there must be a finite displacement, then only we'll say that the work has been done. Why do I say so? I say so because the work that we are talking about has a primary formula as F dot S. That means it can be obtained as a dot product or a scalar product of force and the displacement vector. Now if I expand this, as you all know, if I expand this formula, what I'll get is Fs cos theta. I'll get it as Fs cos theta. What does this mean? This means that suppose there is a force vector F produces a particular displacement, say S vector, and the angle between the two, the smaller angle between the two is theta. So what is theta? Theta is the smaller angle between the force and the displacement vector of the object. Now what are the possibilities? Let us analyze this formula first. Class, there are three major possibilities that we are going to discuss. Possibility number A, theta may be 0. Possibility number B, theta may be 90. And possibility number C, theta may be 180 degrees. What is meant if theta is 0? Theta 0 means force and displacement, they are parallel to each other. Means the direction in which the force has been applied, in the same direction the displacement of the particle is taking place. The direction in which the force has been applied, in the same direction the displacement is taking place. For example, if I talk about a block kept on a horizontal table, and what you do is you apply a force F on the block such that the block displaces to a new position. Let this new position be shown with the blue marker. So you can see the displacement of the block is in the same direction, S vector, right? In this case, we say the force vector is parallel to the displacement vector. Now since cos 0 is 1, therefore the work done will come out as Fs. It's not important to know if it will come out as Fs, rather it's important to know that we call this as positive work. For example, suppose we talk about a ball falling under gravity. एक practical example पे आता है. What happens when a ball is falling under gravity? The force, that is the weight of the ball, mg, is acting in the downward direction. Consider this diagram. Suppose there is a ball which is falling under gravity. The weight of the ball is acting in the downward direction, mg, and the displacement of the ball is also taking place in the downward direction. So you can see force vector and displacement vector, they are parallel to each other in this example. Hence, the work done will be positive. So an example of positive work can be stated like this, or it can be stated in this manner. That is for a ball falling freely under gravity. What will happen if theta is 90? This was a condition which was stressed upon when a child is in class 9th. we say here the force vector is perpendicular to the displacement vector, and since force vector is perpendicular to the displacement vector, then theta is equal to 90, and we know that cos 90 is 0. We all know that cos 90 is 0. So since cos 90 is 0, therefore work done in this case will be 0. We call this as 0 work. Do we have examples in this category? Yes, we do have examples in this category again. Consider this one. Suppose there is a load. I am giving the same example that we had done in class 9. Suppose there is a load which is being carried on the head by a person in the horizontal direction. So the load is being carried in the horizontal direction. Displacement is going to be horizontal, that is along x-axis or on the right. But the weight of this block mg, that is the force vector, is acting in the downward direction. You can see theta is 90 between the force vector and the displacement vector. Therefore work done in this case will be 0. Class, we can consider one more example. Na? Suppose we have a sun, sun, then there is a circular orbit in which there is a planet which is going around the sun. There is a planet which is going around the sun. You know, there is a gravitational force of attraction between the sun and the planet, and this force is acting in the radially inward direction. This force is acting in the radially inward direction. Now if you talk about the displacement of the particle or the planet, the displacement is tangential. The displacement is tangential. Now since the displacement is along the tangent and the force vector is along the radius, therefore theta is again 90. Hence work done in this case will be again 0. So work done by the gravitational force in case of rotation of planet, rather revolution of planet around the sun, is 0. Now moving on to the cases of negative work. What will happen if theta is 180? If theta is 180, then the force vector is opposite to the displacement vector. Now everybody knows, I suppose, that cos 180 is minus 1. What is cos 180? You know, cos 180 is minus 1. And since cos 180 is minus 1, in this case, work done will come out as, W will come out as negative Fs. We call this as negative work. Are the examples present? The answer is yes again. Suppose you have a block or a mass and you throw this mass in the upward direction against gravity. So displacement is in the upward direction, force vector mg in the downward direction. You can see the force vector and displacement vector, they are opposite to each other. So when an object is thrown against gravity, the work done by the gravitational force is negative. Now let us take one more example again. Suppose we are talking about an inclined plane and there is a mass kept over it. The mass is slipping in the downward direction. So displacement is parallel to incline in the downward direction. Displacement is parallel to incline in the downward direction. Frictional force will oppose the motion of the block in the downward direction, and this friction will be acting parallel to incline but in the upward direction. So this is my force vector, you know. Frictional force is the force vector and displacement vector is parallel to incline in the downward direction. If you compare the directions of these two, you see they are opposite to each other. So again, work done by friction in this case is negative. That means, talking about three broad categories, work done can be 0, work done can be positive, work done can be negative. I have stated few examples here. Examples can be numerous, but I have stated few examples. Do remember at least one or two examples for each of the category. One more question before I remove this, I'll answer. Is it the only formula f dot s through which work done can be evaluated? Is it the only formula through which this work done can be evaluated? The answer is no. There are more. So when to use this one? We'll be using this one, or this formula is to be used. Remember that if your force vector F is constant, means if the force is constant in magnitude and direction, then only we'll be using this particular formula. So on the basis of this particular formula, we had three categories as I have discussed on the board. Now I'll be moving on to the other possibilities or the other formulae through which your work done can be evaluated. See, since work is a product of force and displacement, hence the second method to evaluate the work is by finding the area under graph for force and displacement. So method 2 to evaluate the work done. W can also be evaluated by finding the area under Fs graph, that is force displacement graph. And since you know work is a scalar quantity, so all areas positive. All areas are positive. Whether they lie above the displacement axis or they lie below the displacement axis, all areas are to be treated as positive. So sum up all the areas which are given to you in the graph, and that will give you the work done. No? For example, if I talk about this category, now in this case the force may be variable or constant, hardly matters. Just look at this one. Suppose we take force vector on y-axis and displacement vector on x-axis, and they say the graph is somewhat like this. No? The graph is somewhat like this, where the displacement varies from 0 to say S1. So the total work done in the process would be the area of this section, the area of this particular section. But इसका area कैसे निकालेंगे? See, that's what I told you. The force may be constant or it may be variable. If it is constant, you will be getting regular geometrical shapes in the graph. So the areas can be evaluated. For example, we are getting a right angle triangle. It is half base into height. We are getting a rectangle. The area is length into breadth. We are getting a square. It is L square. We are getting a trapezium. So half sum of parallel sides into perpendicular distance between them. Area can be evaluated. Now, this will happen when the force is constant. But if the force is variable, the graph may be somewhat like this. How to find the area of this? Another method, and that is, if force vector varies, then your work done will be W equals to integration. Then we have to apply the integration method. F dot dx from x1 to x2. From x1 to x2. That means the displacement is changing from x1 to x2 with respect to origin for the particle. अब इसको समझ लेते हैं किसी एक एप्लीकेशन में. The example in this category can be spring force. You know, spring force is a force that is not constant, rather it varies. We have the formula F equals to kx. We have the formula F equals to kx. So if you are solving the amount of work done in elongation or compression of a spring, how to find the work done? See, in this case we say F is proportional to x. K is constant, known as spring constant, you know. But x we can alter, and if you alter x, that is the amount of compression or elongation, the value of force will change accordingly. So in this case, force is not constant, rather it is varying. What will you do if the force is varying? Simply, we are going to apply the integration method. Let the spring elongate from 0 to x. This will help us in putting up the limits. That means the initial elongation or compression in the spring was 0, but the final elongation after stretching or compressing a spring is x. So just use the above formula that I have given you. So work done equals to integration f dx from 0 to x. The limits will change as 0 to x. Put the value of force, that is kx dx from 0 to x. So we'll take k being constant outside, we are left with x dx from 0 to x. Now integrate this. So work done equals to k, integration is x square by 2 from 0 to x. Apply the limits. So w equals to half k x square minus 0, or simply half kx square. So this is the work done by the spring force. If you ask me how, limits कैसे लगाया, तो in place of x, if you place x, you'll get it the same value, that is x square by 2. But if you place the lower limit, in place of x, put 0. So 0 square by 2 is 0. So with the upper limit, I get this value half kx square, while with the lower limit, I get the value 0. Hence, upper limit minus lower limit will produce or yield the result half kx square. So work done by the spring force is half kx square. This has to be remembered. Number one, this has to be remembered. And number two, you have got a method how to evaluate the work done if the force is varying, right? Class, these were the evaluations. Still here, these were the evaluations of work done on the basis of the nature of force or the angle between the force and the displacement vector. Now we are moving on to the second category. The forces may be conservative or non-conservative, and on the basis of these, the work done evaluation differs. So let us discuss about the conservative and the non-conservative forces now. I'll be discussing about these forces in two columns. One column I'll take up with the conservative force, while in another column I'll take up with the non-conservative force. So first column, let us take up with conservative force, right? In the second column, let us take up with the non-conservative force. Now when do we say that the force is conservative? Students generally have this trend or definition in mind: whatever is conserved is conservative, whatever is not conserved is not conservative. No, that is not the category, that is not the difference, right? You have to move like this. Number one, a force is conservative. A force is conservative if work done by the force is displacement dependent. If work done by the force is depending upon only the initial and final position or only upon the displacement, then the force is said to be conservative. And a force is said to be non-conservative if work done by the force is distance dependent. See, sometimes this can be also stated in another manner. In this case, we can call it as path independent work done. In this case, we can call it as path dependent work done. So I'm going to write it as with the oblique sign. A force is said to be non-conservative if work done by the force is distance dependent or path dependent. That is, it depends upon the nature of the path that has been taken up by the particle to move from one position to the other. But in this case, with an oblique sign, I can write a force is conservative or is said to be conservative if work done by the force is displacement dependent or path independent. That means in this case, it does not depend upon whatever path has been taken up by the particle to move from initial position to the final position. Are there examples? Yes, the examples are. Example in this category: work done by the gravitational force or force of gravity, Example, gravitational force or force of gravity. Or we can call another force as electrostatic force, etc. The work done by these forces is actually displacement dependent, while the work done by the frictional force or the air resistance, these forces fall into the category of non-conservative forces, since the work done by these forces is dependent upon the nature of the path traveled by the particle. I'll illustrate this through a diagrammatic example, and the diagrammatic example will serve as point number 3. See, suppose let us talk about stairs. We encounter them in our daily life, na? So under conservative and non-conservative for both, point number 3, suppose I take up a diagram where number of stairs have been provided to move from the bottom of this structure to the top. Building ऊंचा हो गया, stairs कम पड़ गया ना. So anyways, building छोटा कर दिया. So suppose we have to move from point A to B. We have to move from point A to B, and what we have to move? There is a mass m that has to be moved. Suppose it's a spherical mass m which has to be moved. Initially it is at position A. Now what you do is you take up this mass and keep it at B. You keep it at B. Now there are so many methods. You may be going via this path, or you may go via this path. So if I talk about force of gravity, then you know the work done will be equal to force of gravity into displacement I said, and that will be given as force of gravity, that is mg for the particle, and displacement. Class, you know displacement is going to be the height of the building h. That means mgh will be the work done irrespective of the path followed. So whether you take up with path 1 or you take up with path 2 hardly matters. In both the case the work done is same. Now suppose we are talking about, or we have to illustrate the work done by the non-conservative force. So point number 3, look for the diagram. If I ask you, suppose there is an inclined plane, and what you do is we have a block which is to be moved from the bottom of the incline to the top of the incline, that is from position A to position B. Path 1 can be this, we are sliding the block from A to B, and path 2 can be this one, we are sliding the block first of all through the bottom, then through the vertical wall. So this is my path 2. Now you know in both the cases the work done is going to be different. If I say h is the height of the incline and theta is the angle made by the incline, so work done by frictional force along path 1 will have work done equals to the force of friction, say F. We are not going to evaluate it, let it be F throughout, right? So F multiplied by the length of the path, that is length of the incline, say L. If you try to calculate this length of the incline, it will come out as say this is L. तो L का वैल्यू क्या होगा जब राइट एंगल ट्रायंगल में आते हैं? This is my perpendicular, this is my hypotenuse, तो h by L equals to sin theta. Hence L will be equal to h upon sin theta. So F into h upon sin theta. This is the amount of work done if we are moving along path 1. Now if you move along path 2, what will happen? Then you know you're traveling through the base and you're traveling through the height. Therefore work done will be equal to F into, what is the length of the base? निकालना पड़ेगा in terms of h. See, this is h, this is base, say B. So perpendicular upon base, if I say perpendicular upon base, it comes out as tan theta. So base is h upon tan theta, correct? So f into base first plus f into height along this. So it is f into base का value निकालो h upon tan theta plus f into h. You see the work done in both the cases is different. The work done in both the cases is different. Therefore frictional force will be said to be a non-conservative force. The forces in which distance is important for the evaluation of work done, they are non-conservative forces, and the forces in which displacement is important for the evaluation of work done, those are non-conservative forces, right? So this was all about the evaluation of work done through different means, through theta, the effect of theta, that is the angle between F and S on work done, the variation of force, sometimes constant, sometimes variable, on work done, and the effect of conservative and non-conservative forces on the evaluation of work done, right? That's all for today's video. This was all upon work. In the next video we are going to discuss about power and energy. By then, just subscribe so that as soon as the video of power and energy is posted, you get informed. Thank you.